In the Roberts example 4-3, we went through what happens with a compressible fluid in this variable volume batch reactor case. And you might have noticed that that was a little bit more complicated for a couple of reasons. One is having to think about how volume is affected by the number of moles in the reactor and how that changes over time in this batch case. Or you can imagine in a flow case, which is why I have the or volumetric flow rate instead of just volume. In a flow reactor, when you don't have the reactor volume changing, but effectively because you're changing the total number of moles, if these are gases, you're going to have a change in volumetric flow rate. How when you have those situations, you know that you're going to have to use a stoichiometric table and then think about mole fraction and be able to relate what was your initial volume to your final volume, or what was your initial volumetric flow rate to your final volumetric flow rate. So I want to be able to essentially make you aware of pattern and get you also thinking about these cases more generally. And just like earlier in the course, we went over this sort of generalized stoichiometric table. Here we'll go over this sort of general relationship between volume and conversion. So I'll first draw this as if it were a flow system, but really these two situations, at least for this concept, are not going to be so different. So we have something coming in, some components coming in and some components leaving. Let's say we have then our volumetric flow rate in and a volumetric flow rate out. And so we have a situation where because our fluids are compressible, these two terms are not equal. And so we might have all kinds of components here, like A naught, B. We might also have an inert species. Let's go ahead and write what this reaction would look like. So there's going to be a reaction here, and I want to write it with stoichiometric coefficients so that we can see at least that this is all on a basis normalized to the stoichiometric coefficient of A. So we have A plus little b over little a times B. Those are the reactants yielding products C and D at this stoichiometry of C over A times C plus D over A times D. Okay, and we worked with this before to ultimately come up with a stoichiometric table. Now here, I want to kind of point out that generally when we're interested in the mole fraction of a species, we know it's the number of moles of that species over the number of total moles. And it could also be the molar flow rate of that species over the total molar flow rate. But either way, something that we know that we want is kind of this understanding of, well, how much does the total number of moles, or the total molar flow rate, when we make our stoichiometric table, we're largely interested in what that number is and also how conversion relates to these terms. So the sort of shortcut to recognize here is that you have your number of moles at any given time is equal to, and this is the total number of moles at any given time, is equal to the total number of moles that you started with, plus, and I'm going to use this lowercase delta symbol here, multiplied by your number of moles initially of, in this case, since everything is is normalized to A, which you would treat as your limiting reactant. It's the number of moles of your limiting reactant times your conversion. Okay, so then the real question is then, what is this delta term? Because if we knew that, we could very quickly get to plugging in this term, and then perhaps we could also recognize what we always do with mole fraction, since we essentially just use the ideal gas law to figure out how we can relate concentration to these terms. And so what I want to explain here, I'll try to fit it on the same page, is that delta, as you define from your stoichiometric table, is going to be just d over a plus c over a minus b over a minus 1. And what it essentially is, I'll just change color. It's the change in total number of moles over the mole of A reacted. Okay. So what can we then do with this? Well, if you take this equation and you think about the total number of moles, so I'll just say this is N total. This is an equation of state that is valid at any time. So it must also be valid when you started. So if you just kind of imagine the initial set of conditions, you know, at some point you had an initial total number of moles, and you had that at a given pressure and volume, and similarly an initial temperature. So you could imagine comparing these two and actually performing division to be able to get this relationship when you isolate for just volume. The volume that you would have at any given time is going to be equal to the volume that you started with times the initial pressure over whatever pressure you're at now, times the temperature you're at now over the initial temperature. And again, this is just coming from the fact that you know, temperature and pressure are on different sides of the equation here. Hence, one has the initial state on the numerator, and the other has it on the denominator. And then you've got your NT over NTO. And so we can already see where there's sort of an opportunity to be able to, just thinking about was on the previous page, utilize this sort of relationship of how the total number of moles is influenced by is related by the conversion. And so if we just take that and sort of put it back here, we have you know, NT over NT naught equals 1 plus that mole fraction, since we have everything on a basis of A, times delta times the conversion. And so what that just tells us overall is, let's see if I can still fit it here, is that V, the volume at any given time, is equal to what it started off as, and then you have this pressure and you have temperature, And now you have just 1 plus the mole fraction of A initially times delta times conversion. Okay, and so this didn't get rid of your need to still figure out the mole fraction of A initially, but it does greatly simplify the kind of approach and stoichiometric table that you might want to prepare, because now you don't need any of the terms at the final the final composition. You just need to know what your initial mole fraction was. Similarly, in most of your problems, you're not going to have pressure and temperature also changing. For example, like Robert's problem 4-3, it's isobaric and it's isothermal. So this just immediately shortcuts, these terms become one, and then you just have this clean and quick relationship between what the volume is at any given time and what it was originally. And lastly, maybe this is a good place for me to note that if you're thinking about, let's see, so let me say this is batch variable volume. If instead, so I'll just draw a line here, or for flow reactors, you can hopefully clearly see how this would then just, you can do all the same things, it's just your little v instead of big V. And I could write this in a different order, but I'll just try to keep it in the same order here. You have your 1 plus YA naught delta conversion. Okay, so this is a relationship that takes into account the stoichiometry and terms involved really with any reaction. And so I encourage you, though, to carefully think about if and whether it might still be true if you have an inert term included here as one of the components in your feed. Because in Robert's example, 4-3, I believe he has that inert component. And so you want to convince yourself whether or not you can still use this shortcut, or whether you would have to modify it slightly to account for the presence of that term.